All right, in this particular presentation, same kind of idea. Again, I'm going to kind of give you method, result, and meaning, and hopefully you can type some things up in your own words. You can copy and paste the abstract and kind of summarize things here. The first group of studies I'm going to talk about is from Joe Ledoux. Very interesting studies. If I just took a tone and I turned it on to an animal, a rat, generally nothing would happen to that rat, right? That would be the way. But let's say, just for the sake of example, I turned on a neutral stimulus like a tone, and then I shocked a rat. I turned on a foot shock for the rat. What would tend to happen? Well, the foot shock would basically lead to a freezing response. The organism would have kind of freeze in its cage. It would have an increase in heart rate, an increase in blood pressure, because obviously a foot shock would cause that. So Ledoux, in his studies, basically started pairing the tone and the foot shock together. And after a number of trials, we got classical conditioning. The tone itself led to the freezing response and the increased heart rate and blood pressure. And so what Ledoux was interested in figuring out, he called this the conditioned emotion response. And he was trying to figure out, well, I wonder if there's any underlying neurobiology for how a tone and a foot shock could work together. And what he basically found is that the key structure in the brain, and pointed out on page 439 of your textbook, is the amygdala. It seems the amygdala is the key emotion center of the brain. It's part of the limbic system. And what he basically did is, in the next group of studies, he took a pathway that went from the amygdala to the periaqueductal gray, and he severed that. He cut that connection. And when you destroy that particular pathway, what he actually found was the whole classical conditioning for the freezing response was lost, because the PAG obviously has a lot to do with pain and pleasure and the freezing response. So he lost that. And then in another series of studies, he destroyed a pathway from the amygdala to the hypothalamus. And when you destroyed that, the heart rate and blood pressure increases from the classical conditioning were lost. So it appears that the central nucleus of the accumbens, as the figure kind of shows there, figure 1213, is really very important in classical conditioning. This is a major study in terms of kind of the mind-body reductionism. Can we take emotions that happen, condition emotional response, and can we link them to biological entities in the brain? So if you can kind of summarize that in your own words, use the information I have there, that would be good. The next study that I wanted to talk about is a study that's, I think, in your book, page 519 of your book? Very famous studies done by Eric Kandel with sea slugs. Let's see if I can find the page. There we go, on 518. Let me kind of describe for you basically what was done here. Basically what was done, in a very simple way, he took the sea slugs and he basically touched their mantle shelf. And if you just touch their mantle shelf normally, you won't see much of a response at all. There will be very little of anything, as 519 talks about. But then in phase 2, what he would do is he would actually deliver an electric shock to the tail, and at the same time do that same thing, that weak little shock, that weak little touch to the mantle shelf. And so when he paired these up in phase 2, in phase 3 he went back to the weak touch to the mantle shelf. And what he basically found in phase 3, when he did the weak touch to the mantle shelf, is you got a huge response just for a weak touch to the mantle shelf. Why? Well, the idea is, once again, this is kind of classical conditioning. If you actually shock the tail, you'll get a huge gill withdrawal response. But it seems that pairing up the shock to the tail with the weak mantle touch caused some classical conditioning. And so what he wanted to see, and if you look on 518, it goes into a ton of detail there. You don't need to know all that. But he basically found that there was an interneuron that basically connected the mantle shelf touching with the tail shock. And when you do those at the same time, you strengthen the connection. And so the idea that this interneuron for the weak touch to the mantle shelf, the UCS, can actually change everything around is what he came to the conclusion of here. So this is kind of neuroscience-based classical conditioning stuff. You can take something very simple, and if you pair it with something very severe, he's been able to find kind of the mind-body link, the type reductionism, much like our previous researcher, Ledoux, and figure out, okay, here's exactly what's going on. So the bad news is, in this case, that we kind of have reductionism here, that when you think you're getting totally scared by something, your brain is actually changing its connections to allow this as well. The final situation I wanted to describe for you briefly is something that's gotten a lot of excitement in the field of neuroscience. It's a phenomenon called long-term potentiation, and I'm going to give this a brief bit. Your book has a lot more detail. You don't necessarily have to go that far. You can just add the acoustics and read the book and see if it makes some sense. Same kind of idea with long-term potentiation. No one researcher here because there have been so many that have done things. So in stage 1, what they basically do is they work with, let's see what we got here. I'm trying to see if they work with species here in this particular study. I don't think it's sea slugs here. I'm forgetting the species they're working with. I'm trying to read it in your book here. But they basically take fibers from a part of the brain called the hippocampus. And of course the hippocampus is very important in memory. And what they do in this study is they go in to the hippocampus area, and if they take a presynaptic area of the hippocampus and they just do a small little stimulation presynaptically, and then they measure out the postsynaptic response. And actually, if you look in your figure 14.21, the pathway is kind of CA3 to CA1. CA stands for corno-ammones. CA and corno-ammones in Latin stands for seahorse, because the hippocampus looks like a seahorse, according to neuroscientist people there. So they stimulate presynaptically in CA3, and they find they get a small response postsynaptically in CA1. That's stage 1. In the second stage of the study, they basically do high-frequency stimulation presynaptically. That's called tetanic stimulation. They deliver a whole lot of juice to the presynaptic area here. And of course, if you deliver a whole lot of juice presynaptically, then postsynaptically you see a whole lot of firing. Those are called EPSPs, a lot of excitatory postsynaptic potentials. The most interesting thing, though, is what happens if you go in either a couple minutes later or any time really up to 3 or 4 days later. If you go in even a couple days later and then just put a single little pulse back in, the simple electrical stimulation, you actually find that you get a huge postsynaptic EPSP response. So this is the same kind of idea as Candell and the sea slugs, the idea of you do something small, nothing happens. You do something large and it changes everything, and then do something small again, and it seems like you get a huge response. This physiological phenomenon is called long-term potentiation. And the reason it's got everybody in the field of neuroscience in kind of an enlightened state, I guess I should say, is they're thinking this might be what occurs when you memorize information. And I'll just give you a little analogy here. They think this might be what occurs when you memorize information. Let's say that you're studying for a test. Let's say you really cram and you really try to learn as much as you can. You might call that, as a metaphor, tetanic stimulation. You show up to the test, you get one simple test question. What do you hope happens? Cognitively, you hope that everything kind of flashes back on that. So that's kind of the idea behind this mind-body link. They think that this physiological phenomenon of long-term potentiation might be exactly what's occurring when you go through the cognitive process of memory. This study is in the field of cognitive neuroscience, how cognitive things relate to the brain. Now, some people believe that long-term potentiation might be what goes on when you memorize, but there are a lot of people actually who believe that it's just physiological and really isn't what happens when you memorize information. So from these 3 studies, hopefully you can kind of go through, summarize, copy and paste the information there, summarize what's going on, and give me kind of the big picture idea of each one of these. Thank you very much. Bye-bye.